Okay, welcome to week 4, and got a little scruff going. I don't think I gelled just right today, but anyway, we're here. So uh, let's get into the show a little bit. So what I have done, I've everything in week 3 is open. So the only two things there to do are to finish the homework, finish the thermo. If we have time, the thermo quiz. If we have time, we'll dig back into that. Today, though, I just want to move on to background fundamentals. So we'll just kind of click through each thing in turn. You're going to read pages 24 to 56. So read pages 24 to 56 of Chapter 2. Chapter 2 is kind of the biggie. Lots of good stuff in there. We'll breeze through the lesson notes, pick up on what's important. This is these are Brian Kern's words, but it's true for most people. Organic chemistry is usually not everyone's favorite. The strange thing is, though, that organic chemistry is relatively simple in terms of the number of players. It's usually just carbon and hydrogen. Sometimes you'll see some oxygen, sometimes some phosphorus, sometimes some nitrogen, but that's basically organic chemistry, carbon and hydrogen. The alkanes, they start off with methane, go on up. So methane, ethane, propane, butane. Hep is hexane. I don't remember what's 5.
Propane, butane,
Pentane. Yeah, pentane. You don't think of. Yeah. So that's relatively straightforward. I'm just talking about a backbone of carbon with the hydrogens saturating it. Alcohols, you've got an extra oxygen. Basically, you just got an extra oxygen hanging out where you used to have a carbon or an OH. Okay. So look at table 2.2 on page 28. So what an ester is versus an ethyl, and really we're just changing vowels around to mean different bond types, usually double versus triple bonds versus single. Triglycerides, we'll get into that with fats and biodiesels, again carbon, hydrogen, oxygen. There's a formula for triglycerides on page 48. Sugars for making ethanol, again all hydrocarbons. Lignocellulose, this is, these are the big structural polymers that make up trees. Quite complicated in structure and not always the easiest to break down if you're trying to make gaseous or liquid molecules. Okay, so that's it. Favorite organic compound. Favorite organic compound. What is my favorite organic compound? A couple of years ago it was thujone, because Blue Marble Biomaterials here in town was making a thujone out of some pine tree, some cedar they were harvesting up from Lubrecht and distilling it. Favorite organic compound. Do you have a favorite? Everyone likes alcohol. Everyone likes ethanol. Oh,
It's not my favorite.
yeah, no. I don't want to get too complicated with it. I'm a pretty big fan of cellulose. I'm just going to be boring and say cellulose. Cellulose. I'm just going to say check out the molecular pathways for cellulose. Basically starts with sugars, go through starches, but it's kind of a cool thing to look at how cellulose is built. It can basically be as long as you like. Okay, so let's go back here. I posted my discussion. Cellulose. Get back into week 4. Yeah, this is a really good course. All right. Well, let's just take a look at the example problem. I don't think this is going to be too daunting. Okay, example problem. Okay, organic compound. Let me just see your textbook to make sure it is the same. Page 25. Second figure. Yeah, okay. So, yeah, so we're going to look at, they look slightly different, but this is the guy we're looking at right here with that double bond, double carbon bond, and then there's your oxygen right there. So it's just shown a little bit differently.
Turn.
Right, it's just rotated. It's rotated about 180 degrees. So it's not identified in the text. Let's try to figure it out. So by simply counting the atoms, we get the molecular formula of C6H10. So let's just count them up. There's 1, 2, 3, 4, 5, 6. So each one of these little elbows is a carbon. So 2 of them are labeled and 4 of them are not. So there's your C6. Now, this bond out here is saturated. So it's got the 3 hydrogens. There's a carbon sitting right here. And it's worth noting that that carbon bond, and we'll just review that again briefly. The carbon bond. I love the dynamic periodic table. And I love going into the orbitals. So there's carbon. So again, the way to look at this is there are 1, 2, 3, 4 electrons missing from carbon. So there are 4 places to bond. In the case of hydrogen, there's just the 1 right there. And then there's this guy. Oxygen has the 2. You can think of this in 2 ways. Either there's 2 missing or there's 2 extra. So either way you think of it, they're the 2 electrons that oxygen has that are attaching it to carbon. The double bond right there. Okay. And then, so where are the hydrogens? Well, 1, 2, 3. There are none here because it's saturated. So 1, 2, 3, 4, 5. Because this carbon bond only has 2 bonds currently. 1, 2, 3, 4, 5, 6, 7, 8. There's 1 there because 1, 2, 3. There's a 4th line missing. 8, 9, 10. So there are the 10 hydrogens. Okay, it's also found that the bond line structure, right-hand image, we can see that in comparing with the functional group on table 2, that this is a ketone. So let's just go out and look up the definition of ketone. Go look that guy up. So we have the oxygen sitting there, indicative of what we see right there. So is that sufficient to make it a ketone?
Oh. The oxygen is
So right here is acetone, which is the simplest. So the position of the double oxygen bond or the carbonyl group doesn't matter. It's there. It's just there. So you can see that it can be a lot of different places. There it's in the middle, there it's near one end, there it's near another end, there it's hanging off on the side, on the other side. There's a pair of them. So there's acetone, oxaloacetate, acetylacetone, right there, acetylacetone, cyclohexanone,
That's that one on the end,
that's this guy. No, I'm sorry, that's so acetone, oxaloacetate, acetylactone, cyclohexanone, yeah, because there's 6 carbons, cyclohexanone, precursor to nylon, that's kind of fun. Muscone, an animal scent,
Okay.
musk, a little musky there, yeah. And then tetracycline, antibiotic.
Wow.
So it's kind of weird to think, oh, well, it's just a molecule, right? It's got this name, tetracycline, but there it is, antibiotic. Kind of cool. Okay, so that's how the bonding works out, and that's what a ketone is. And it's called a functional group just because that's what allows that ketone to do its thing. It says take a note between the difference in ketones, aldehydes, and ethers. So let's go and look at the aldehydes too. Yeah, so in this case, the aldehyde is always at the end. So that is key to understanding it. And so when you see the ketone, it's the carboxyl group is not adjacent to a hydrogen, as it is in an aldehyde. So those neat little pictures say, okay, there it is. That double oxygen bond is there, and it's near the end. It's adjacent to a final hydrogen bond somewhere. So there's your aldehydes. And you might say, well, all aldehydes are ketones, but not all ketones are aldehyde. I mean, you might think of it that way. That's not exactly true, but that's one way to think about it. Because they both have double oxygen bonds. It's just that the ketone is buried somewhere, not next to the hydrogen, right? And then finally, let's look at the ethers. And the ethers, I'm liking these pictures. I thought there would be more. So all three, the ketones, the aldehydes, and the ethers all involve an oxygen, but in this case, the oxygen it's in the middle.
What was the last one?
This is the ether? Ethers, yeah. So here's an example, but the oxygen is almost always bonding some carbon on each side. The oxygen is just holding those guys together. Yeah, this is some kind of neat things on its structure. Okay, so we got those guys all nailed down. So 6 carbons in a long chain, so it's a hexane. Start there. And then there are 6 carbons in a long chain, so it's either a hexane, a hexene, well, there we go, or a hexyne. Okay, so so if it's an ane, you've got single bonds. So so you might just make a note, A is single. Ene is a double, and we can see there is a double bond, or an ine
It's triple, right?
is a triple, exactly. So the bond line structure shows a carbon-carbon double bond, means it is a hexene. There we go. Below is another equivalent representation, basically just a flipped. Okay. So naming these guys can be a daunting task, but there are rules, lots of exceptions. The carbon double bond makes it the functional group in this molecule. We usually begin specifying the location by counting from the carbon end closest to the functional group. So in this case, the double bond occurs on the first carbon. So this is the functional group. Sort of defines the properties of the molecule. Counting from the carbon end closest to the functional group. In this case, the double bond occurs on the first carbon. So this is carbon number 1. So we're just going to call this 1-hexene because the double bond occurs on that carbon. But there is a second functional group, and it's in the fifth. So there's 1, 2, 3, 4, fifth carbon, and there's the sixth one, of course. Right, so, and it's a ketone. So here we go. So 1-hexene, well, there's your E, otherwise it'd be hexane, 5-one. 1-hexene 5-one is the technical name. Because the 1 refers to where the carbon is, that's your double bond, and then 5 is where your ketone is, and that's the ONE. Or allyl acetone. Okay, so we're not going to have to go through this, but it's just, we went through the exercise. And if we go through allyl acetone, images, there it is. But let's see what it might be good for. Flavoring agents and cosmetic fragrant accent agents. So this guy must has a neat, yeah, it has some kind of smell. No benzene, just a smell. Yeah. Okay, so there's the example problem for the week. Let's just take a look and see what else is, what other goodies are here. So, week 4 homework. Okay. So combustion equations, reactions figured prominently. Review the fundamental combustion reaction in the textbook. This is equation 2.3. Can I just see that guy really quick? Thanks. On page 14. Oh, so that's just the methane combustion equation. Compose a similar for octane. Oh, and you can throw nitrogen in there too. But the nitrogen, of course, does not react. So, all right. Well, we got a couple days to do that. So 7 days left to knock that out. So it's just basically taking that methane reaction. Yeah, and I think I can even. So we've got CH4 plus C, plus O 2. And then the question is, what does that yield? So we know that the two products are CO2 and H2O. This is fairly straightforward to balance. So what I start with here is to say, well, the carbons are already balanced, right? So you have one carbon on each side, so no need to mess around there. There's 4 hydrogens on the left, so we need 4 hydrogens on the right, so we'll just add a 2 to that. I'll just show all the steps here. Copy, paste. So 2 hydrogens there. This is sort of my next step, and now you scratch your head and say, oh, well, I've got, I have 4. I have 4 oxygens on the left now, don't I? Because I have 2 oxygens here, then I have 2 oxygens there. So I need to up the oxygen content by making that 2. So now I have 4 oxygens on the left. I have 1 carbon on the left, 1 carbon on the right, and I'm done. So that's how you run that guy. If we did something similar, and we started with let's just say C3H8. So this would be propane. We right away we can start off the bat. Since there's the only thing with carbon on the left. So this is methane. This is propane. Just to put that 3 there. And now we have to up our game on the hydrogens. So there's 8 there. We have 4. We've got to make that to 4 total. Yep, now we have 8. So now we have, let's see, 1, 2, 3. We've got 6 oxygens plus 4 is 10. So this becomes 5. And that's really all you're doing to get to your octane. Same little exercise. So that's that. Okay, I'm going to call it good, unless you have anything else.
Oh, I have
Okay.
lots of too.
Super. Thank you. See you next week.